Partial answer key for this year's second semester review, I noticed that many of the force questions weren't answered, so I thought I would bust those quickly. Again, I would encourage you to go back and look at your puck packets, your weight versus mass graph, and maybe review some force diagrams before delving into this. But here are the answers from the second semester review. We had already done the motion stuff with the stacks of graphs on the top of the page. So on number 6, starting at number 6, we've got an object experience a net force must be accelerating, and it must be accelerating in the direction of the net force. An object with no net force either must be at rest or moving at a constant velocity. That's Newton's first law. An object at rest will remain at rest till a net force acts upon it. An object in motion will remain in that motion till a net force acts upon it. Number 8, an object in motion will remain in motion until a net force acts upon it. An object will remain at rest until a net force acts upon it. Net force, sigma F means net force, but it also means the sum of the forces, which means you can literally just add them all up. Number 10, we need to delay from now. That's not something we've learned yet. You had already answered the slope of the position versus time graph is velocity. Moving on to 12, the slope of a force versus mass or weight versus mass graph is the gravitational field strength constant. If you did that experiment on the Earth, that'd be gravitational field strength constant on the Earth. And then lastly, whoops, I can't see where to click that. All right, here we go. How do you find the weight of a 47 kilogram mass on the Earth? Show your work. The first thing you would want to do, let's see, I need this button. The first thing you want to do is start with your general equation. Force of gravity is equal to GCB times the mass. It looks like my gravitational field strength constant got erased, so I'm going to have to come in here with a marker and write this in. So you've got 10 newtons per kilogram times 47 kilograms equals 470 newtons. If you take a look at the units of the way they work this out, I should have picked different colors. The kilograms reduced to 1, so that leaves with just newtons. Moving on to one of the later pages, and I think I'm going to adjust the screen just because it's too difficult to move this around. Well, it let me. It doesn't look like it will. All right, so moving on to side 3. It says, draw a force diagram for the puck at rest on an air table that is turned on. The air table would suggest that it's frictionless. The acceleration would be 0 and the net force would be 0, so what forces would be acting on it? We would have two forces, a downward force of gravity on the puck by the Earth and exactly the same size force normal on the puck by the air. Remember, it is sitting on a surface of air. Number 16, for the puck, it's now moving at a constant velocity to the right. That's an old symbol we used to use for constant velocity to the right on an air table that is turned on. So if it's moving to the right at a constant velocity, it's not accelerating, in which case the net force should be 0. And in this case, the force diagram is going to be identical to the previous problem. So you got force normal on the puck by the air upward and the downward force of gravity on the puck by the Earth, and those are the same size. For number 17, it says draw a force diagram. It says while moving to the right, the air table is turned off and the puck slows. So it's moving to the right but slowing to a stop. So is the acceleration of 0 or not 0? It's not 0. Is there going to be a net force? Yes, there is. So the net force is not 0. The horizontal forces are going to be the same on this. We're still going to have a force normal on the puck upward, but instead of air, because the air table was turned off, right, that's now going to be the surface. And then the downward force is the force of gravity on the puck by the Earth. But because we're now on an air table, there's now friction. So as the puck is moving to the right, it experiences a constant force to the left, which is a force of friction on the puck by the surface, which causes it to slow to a stop. I think there's just one more problem. Draw a force diagram for a bucket of water that's being raised from a well at a constant velocity. The constant velocity tells us the acceleration is 0 and that the net force is 0. There's not going to be any horizontal forces on this one. It'll all be vertical. The upward force is force of tension on the bucket by the rope. And the downward force is force of gravity on the bucket by the Earth. And these two have to be the same size because the net force is 0 because the acceleration is 0. I hope that helps for the force diagrams. And remember, for this season, this is all you've got to take care of. There's no need to do side 4.